Hello, so in this video we will do question number 3 from the old test 3. This question just asks you whether you know if the series is convergent or divergent. So the first question is the sum and goes from 1 to infinity. 3n squared minus e to the power of 8n over 2 times e to the power of 8n plus 4n minus 1. So what did I say in class? Always think about the test for divergence. Check what is happening with the sequence an. If the limit of an is not 0, then by the test for divergence we conclude that this series is divergent. Okay, so the limit of an is just the limit of 3n squared minus e to the power of 8n over 2 times e to the power of 8n plus 4n minus 1. And now here we're going to factor out the leading term. Okay, so in that case that would be the exponential e to the power of 8n, 3n squared over e to the power of 8n minus 1 over e to the power of 8n 2 plus 4n over e to the power of 8n minus 1 over e to the power of 8n as n goes to infinity. And here we cancel out that leading term. Okay, from the classes so far and from the video uploaded already, what do we know is that the exponential functions go much faster to infinity than any polynomial of any order, which means that this quadratic over the exponential will go to 0 as n goes to infinity, and by the same logic these will go to 0, which means that this limit is simply -1/2. Well, -1/2 is not 0. And here write down the conclusion. By the test for divergence, the sum of an is divergent. Part B, n minus 1 over n. Of course, you can always, n starts with 3, and that will play a significant role in this particular question. Of course, you can do here test for divergence and figure out what is going to happen with an. So that's the limit of ln of n minus 1 over n. This ratio here tends to 1. So we have ln of 1, which is 0, which means that the test for divergence is inconclusive. Okay, well, we talked quite a lot about this series, that this is nothing else but the telescoping series in disguise. Okay, so the telescoping series is being, we prove whether the telescoping series converges or diverges by writing out what is Sn. Now, just to remind you, Sn is the nth partial sum, so that's a1 plus a2 plus a3 plus a4 plus and so on plus an minus 1 plus an. Okay, and now we're going to expand this, but before we do that, I need some explicit difference in an. So an needs to be written as bn minus 1 minus bn, let's say, or some version of that. And by properties of logarithms, if you remember, by properties of logarithms, ln of a over b is equal to ln of a minus ln of b. So that means that this is the sum of ln of n minus 1 minus ln of n. And starts from 3 and goes to infinity. Okay, so let's write down what is going to be a1, right? So here on the side, I'm just going to write that an is this term here, ln of n minus 1 minus ln of n. When n is equal to, be careful, now we start at 3. When n is equal to 3, I have 3 minus 1, that's 2. So ln of 2 minus ln of 3. This is a1. Plus, now, a1, right? But that's when n is equal to 3. Now n is equal to 4. So ln of 3 minus ln of 4, this is a2, plus ln of 4 minus ln of 5, This is, maybe we can write them like this so it's going to be less confusing. And then we go all the way to the last one, an, and an is explicitly written here. ln of n minus 1 minus ln of n. So what can we cancel? We cancel this one and this one. ln of 4, ln of 4, ln of 5 will cancel with the next one. And what do we have? We have one term left at the beginning of the partial sum. That means that we'll be left with one term at the tail of this partial sum. Okay, so finally I can write that as n, after we develop it and after we cancel everything, boils down to ln of 2 minus ln of n. Okay, so there are some questions in the past finals where they say write down explicitly the nth partial sum, or give an explicit expression of the partial sum. Okay, and this is what you have to do. You have to expand it and cancel everything. Now, in order to prove whether this is convergent or divergent, you have to know the definition of infinite sums, and that's that the sum of an as n goes towards to infinity is equal to the limit of the nth partial sum as n goes to infinity. Okay, and of course, also this definition pops up quite a lot in the past finals. Well, this is the limit as n goes to infinity of ln of 2 minus ln of n, and this is simply negative infinity because this is a constant. Minus ln of n goes to infinity. Okay, and now here I'm not using some particular test. Here, obviously, I have found exactly how much is this sum. This sum is negative infinity, and hence it is divergent. Question number C. ln of 1 minus 1 over n to the power of n as n goes from 1 to infinity. Okay. Again, always do the test for divergence. Very quickly, let's check what's going to happen. Limit of an is the limit of ln of 1 minus 1 over n to the power of n. So here it's n, sorry about that. Okay, so the base goes to 1, the exponent goes to infinity, as n goes to infinity. Now, of course, in that case, you can use the whole procedure of how to evaluate this indeterminate power, right? 1 to power infinity, or simply I've told you how much this limit is going to be. So this converges to what? This will converge as n goes to infinity to e to the power of negative 1. Be careful of the sign in front, right? So this is e to the power of negative 1, and this is simply negative 1. Well, negative 1 is not 0, which means that the test for divergence works. Sum of an is divergent. Part number D. 1 over n square root of n squared minus 1, and goes from 2 to infinity. Okay, very quickly test for divergence. Limit of an is limit of 1 over n square root of n squared minus 1. This is obviously 0 as n goes to infinity, which means the test for divergence is inconclusive. Okay, so what are we left with? Here, the best way to approach this problem is to use one of the comparison tests. So compare it, sum of an with sum of, and now you have to come up with this. Now you have to come up with bn, right, with this sum. And I'm going to choose 1 over n times square root of n squared. Okay, so I just choose the highest exponent in the numerator and denominator. In the numerator is just a constant, and in the denominator is this. If you simplify this, you get 1 over n times n, which is 1 over n squared. And here you should know that 1 over n squared is because I'm using one of the comparison tests, so this is going to be Convergent P Series. Okay, so if I'm able to show that an is less than bn, if I can show that an is less than bn, then we're done. We just use the comparison test and we're done. But this actually doesn't hold here. Okay, be careful. An is 1 over n times square root of n squared minus 1. This denominator is less than this denominator. Why? Because here I'm subtracting 1. If this denominator is less than this denominator, the reciprocal will flip the sign. Okay, so as you can see, the comparison test doesn't work. I don't have the needed inequality. Okay, then we move on to the limit comparison test. Of course, here you don't have to go first. You don't have to check this. You don't have to go first through the comparison test, and then if it doesn't work, you go through the limit comparison test. If you want to start with the limit comparison test, just start with that one. The limit comparison test says find the limit of the ratio an over bn. And I will let you solve this by yourself. Okay, this limit is 1. Well, 1 is greater than 0, which means that by the comparison test, by the limit comparison test, both sum of an and sum of bn act the same. Both of them behave the same. But since I already know that sum of bn is convergent, sum of an by the limit comparison test has to be convergent. The next question is somewhat similar. Sum of n minus 2 to the power of n over n times 2 to the power of n. Okay, so again here I'm gonna go for the here I don't know what am I gonna do. Okay, so I can go through the standard way of comparing this. N goes from 1 to infinity, and I compare this and then I say, okay, let's say negative 2 to the power of n over n times 2 to the power of n. These two can be cancelled. I have negative 1 over n. I can factor out the constant 1 over n, and this is, I need you to write this divergent harmonic series, which is nothing else but the P series when P is equal to 1. Okay, so if sum of bn is divergent, then in order to use the comparison test, I want this inequality. I want to be able to show this inequality, but I don't know if it is true. Okay. Okay. Note that n is positive. N is greater or equal to 0. Okay. So bn is negative 2 to the power of n over n 2 to the power of n. If I add the positive number to this one, that sum will be greater. So if I add positive number to bn, this number will be greater than Bn, and this is just An. And there you go. The comparison test works. By the comparison test, sum of An is divergent. Why? Well, we have shown that An as a sequence is greater than Bn, and on the top of that we have shown that sum of Bn is divergent, so that means that sum of An also diverges. The next question is the sum as n goes from 1 to infinity of 3n minus 5 over n squared minus sine of n. Okay, if you take the limit comparison, the test for divergence, which you could have done here also, the test for divergence would have been inconclusive because this limit is 0. Okay, so that leaves me only with the choice of sum of the, of course you can use the any given test for positive series, but I will use the comparison test. And I'm going to compare this with 3n, the leading term in the numerator, over n squared, the leading term in the denominator, which is 3 over n, which is 3 times the sum of 1 over n. And 1 over n is harmonic, which means they're divergent series. Okay, so I'll do the limit comparison test here first. Somebody might say, well, why? How did I know just to start with the limit comparison test? As I said, it doesn't matter. You start with, when you start with the comparison or the limit comparison test, that's up to you. So what do we have? We have the limit of An over Bn, that's equal to the limit of 3n minus 5 over n squared minus sine of n times the reciprocal of Bn. And the reciprocal of Bn is n squared over 3n. So let's solve this limit. I factor n from this factor. That leaves me with 3 minus 5 over n times n squared. And I factor n squared from here. And I have 1 minus sine of n over n times 3n. So n squared cancels with n squared, n cancels with n. Okay? 5 over n, as n goes to infinity, this approaches to 0. Okay? So and then sine of n over n, n doesn't go to 0, so don't mix this limit with sine of theta over theta where theta goes to 0. Sine of n over n as n goes to infinity tends to 0. Why? Because sine of n is between -1 and 1. If you divide both sides by n, -1 over n less or equal to sine of n over n less or equal to 1 over n, these will go to 0, so sine of n over n goes to 0. So this one here goes to 0 also. So what are we left with? This limit is 3 minus 0, which is 3, over 1 minus 0 is 1 times 3 is 3, which is 1, which is greater than 0. And by the comparison test, these two sums behave the same. Also diverges, right? Behaves like the sum of Bn. So here you're going to write this is divergent. Okay, in the next video I will finish this problem.